So we're going to have a look at two source interference, which is something we did do in standard level. And we are going to derive Young's double slits equation and apply that relationship. We're also going to look at some more qualitative aspects of two source interference. And so just to remind you, just a quick visual of what this idea of interference looks like. It's to do with progressive waves, so waves that travel, and what happens when they meet. So I'm going to first review the idea of constructive and destructive interference. And so here we have some waves, two waves, which are in phase with each other. And so what's happening here is what we call constructive interference, where the wave amplitudes add to create a final wave which is much greater in amplitude. And so this would be your area of constructive interference. Destructive interference would be when the wave amplitudes are aligned in such a way that the overall amplitude is then much smaller. And in fact, if these two waves happen to be the same but opposite in orientation, you will end up with nothing, which is a completely destructive situation. And so now if we have a look at the water waves again, you can see that there are some really nice examples, areas you can see here, right? These gaps where there is destructive interference. What's happening is that the waves, the crests, the top part of the wave, let me just do a bit of vocab there. The top part of the wave, which is called the crest of one, meets the trough of another, right? And so we'll see that here, and they cancel, and you get an area where there's no wave at all, and that's called destructive interference. Now, when you use two sources, you get a very distinctive pattern, and by two sources, that simply means like two sources or places where coherent waves will originate. So in this case, we're looking at water. The most common situation for IB is light. And this is what you end up with when you have two light waves interfering with each other. You end up with this arrangement of maxima and minima, or bright and dark fringes. So let's have a look at that. Using the same analogy as of the water waves, we are now going to refer this to light. And the way that you would get interference with light waves is by having a single source of light, say a red laser. That's something that we actually did last year. So you would have your red laser light, which is incident on two gaps. And of course, those gaps cause something called diffraction, the spreading of the wave. And because you're getting that spreading happening on where the both gaps are, it's as if you now have two perfect sources. This is a simple way of creating two coherent sources from one. Now, by coherent means that they, the two waves that are coherent have the same phase and the same frequency, and the same phase difference and the same frequency. So it's almost like they're exactly the same, right? So those two will be coherent because of the two gaps. Now, if you follow this point here, which is where you're getting the crests. So if we have a look at the diagram, you can see that there's crests and they meet. So that is a point of constructive interference. And if we look at our video of the water, you can see that that's quite difficult to catch, but you can see those bits there, right? So where the two waves meet. And that point of constructive interference creates this bright fringe. And where there's in between the bright fringes, you get those areas of destructive. So here you can see that there's a crest, and it hits the middle of these two crests, which happens to be a trough. So that would be your area of destructive interference, your dark fringes. Now we refer to those as maxima and minima, right? So the bright fringes are called maxima and the dark fringes are called minima. Now the arrangement for two sources is has to be instantly recognizable. You've got to be very familiar with it. So they're fairly even, thick maxima lines, and this is distinctive for two source interference. And when we have a look at them like this, we can actually refer to their position as well. The maxima in the middle of the slits, that would be called your zero order maxima. Your next two, these two, would be called your first order maxima, and then the next two, which would be this one and this one, would be called your second order maxima. Okay, and so on. The brightness can be represented on a graph that looks like this, an intensity graph. And what you need to be able to identify is the repeated nature of this peak, representing the bright fringes. Now for double slits, the intensity is very similar. Now, it probably won't make much sense now, but when we compare this to multiple slits or single slit, you'll see what I mean. What's distinctive about this one is that there isn't that much difference from one order to the next, right? And you can tell by looking at them, they don't look very different in terms of brightness. And you represent that in terms of the intensity, the height of these curves, right? They're also equidistant. So the distance between each peak is the same, and you can see that in the bright fringes. So before I go on to the equation, let's see where we are. You hopefully remember now a little bit more about interference, what it means, what two source interference actually looks like, this idea of constructive and destructive bright and dark fringes. You understand how constructive and destructive interference works, and you know what a interference pattern for a double slit situation with light would look like. We haven't talked about this yet. We'll talk about that later. We'll do that next week, I think, or maybe in the next lesson. So don't worry too much about the color aspect. But what I'm interested in is that you understand this kind of diagram and you can interpret this kind of graph. I will explain this last bit, why that's 2 lambda over d, in a moment. But for now, I just want you to understand what that graph looks like. And so now, let's start looking at the more qualitative aspects. No, I got that wrong. Quantitative aspects, the numbers, the number crunching. And you probably recognize, I hope you recognize this equation from last year, which is the Young's double slit experiment formula. And Young's double slit relates to a 2-gap light separation experiment. Okay, so when we talk about double slits using two sources or two source interference, it's the same as Young's double slit experiment. Okay, the actual experiment itself you would have looked at last year, and I think we did do that as a demonstration. So anyway, back to the equation. I digress. So we have S equals lambda d over d. Great. What does everything mean? Well, the big distance, if we look at this diagram, oops, it's gone. If we look at a diagram like this one, you have your two slits, right? Your two sources. So in terms of light, it would be 2 slits. In sound experiments, it would be 2 loudspeakers and the distance between them, right? If it's this experiment here, then it would be the distance between the 2 balls. There we go, those two. That would be your distance between the sources, which is little d. It's a little d because it's a little distance, right? Now, When you see your bright fringes on the screen, if you remember that, this, okay, if you were to position that screen further away, then you would find that this distance between the bright fringes would increase, right? So this distance, which is a very large distance compared to this one, so it's a capital D, is also very important. It's very relevant. So capital D is from here to here, and it's the distance between the source and the fringe projection, or your resulting your where your results land. Okay. Then, oops, we also have lambda. Lambda refers to the wavelength of the wave you're using, and S then is simply the distance between bright fringes, right? So from here, the middle of this one, to the middle of that one, or that one to that one. It's the same. So it's very important that you have a system for remembering what everything stands for, okay? Small d is this small distance, which is between the sources. Big D is quite easy to remember because it's a very big distance. And then fringes, the distance between the fringes is S. So now let's try using that equation. Here's a quick question. We have monochromatic. Monochromatic means that it's pure in the sense that it only contains one wavelength of light, so one color. So red laser light is monochromatic because there's only one wavelength. The slits are 1 millimeter apart, 1 times 10 to the minus 3. They project to a screen 10.5 meters away, and the distance between them is 7 millimeters, 7 times 10 to the minus 3. Get your calculator, see if you can get an answer for that one. Calculate the wavelength of red laser light. See what you get. Stop the video. Hopefully, you got a value of 670 nanometers simply by plugging in the values. Super easy. Now, this equation is the equation that you used in grade 11. Grade 12 has a slightly different equation, this one, for the same thing. And so what we're going to do now is we're going to derive this equation and try and link it back to this one. So see where we got this one from. Now, the derivation begins with this idea of path difference. Path difference is the difference in distance travelled by two waves from their sources to the point where they meet. And you can see from here the two waves leaving this, the gap. So these are your two wave directions leaving each respective gap. These two will meet at a point which is very, very far away. And because of that large distance, capital D, you can assume that the rays are parallel. They're obviously not parallel, but they're close to parallel. So it's a way to help with the maths. If you then assume that the two rays meet to constructively interfere, then you can derive the path difference. These two waves, if they constructively interfere, they must have a path difference equal to n lambda. It's got to be an integer times the wavelength in order for them both to meet eventually at the same point and the same part of the wave. Have a think about that until it makes sense. Why is the path difference? Why does it have to be n lambda? Now, n lambda is not the only way to derive this distance. You can also derive the distance using d sine of this angle. This angle is simply the orientation from the horizontal to the maxima, the point of constructive interference. For that reason, you will get a path difference equal to d sine theta. And that is how we derive this equation. Now, in the next video, I'll explain how this can then lead you back to the equation from last year.